Graphs of equations in two variables, intercepts, and symmetry. So graphs of equations. The graph of an equation in two variables, x and y is usually what we use for these variables, consists of the set of points in the xy plane whose coordinates xy satisfy the equation. Anytime the graph crosses an axis, we're going to call that an intercept. That is, if it crosses the x-axis, we will call it an x-intercept. If it crosses the y-axis, we will call it a y-intercept. We're going to determine whether each ordered pair is a solution of the equation. So I have these two ordered pairs. If we want to know if it's a solution of the equation, what can we do? Well, remember that this is just some x value and y value, and we want to make sure that they make this equation true. And so we're just going to plug things in and check and see what we get. So we have 2 times negative 5 plus 3 times 7. We get that 2 times negative 5 is negative 10. 3 times 7 is 21. And then negative 10 plus 21 gives us 11. And notice that the original equation said that 2x plus 3y has to equal 18. Well, we didn't get 18, right? We got 11. So this is not a solution. Now let's try 3, 4. So replace the same way. 2 times 3 plus 3 times 4. 2 times 3 is 6. Plus 3 times 4 is 12. 12 plus 6 is 18. 18 does equal 18. This checks out. So this is a solution. Like I said, intercepts. The x-intercept, a0, is going to be a point where the graph crosses the x-axis. Now, if someone gives you an equation and says, find the x-intercepts, what are we going to do? Well, let y equal 0, and then solve it for x. Now, just as a refresher as to why this works, remember, if this is my x-axis and this is my y-axis, if I ask you what is the x value on the y-axis, well, it's always 0, right? And then if I ask you what is the y value on the x-axis, well, it's always 0, which then leads us to the y-intercept, which is the point 0b, and it's going to be a point where the graph crosses the y-axis. And to find it, just let x equal 0 and then solve for y. So we want to graph 2x plus 3y equals 18 by plotting the intercepts. So let's find the x-intercepts first. Well, the x-intercepts are going to occur when y equals 0. So to find that, that's going to be 2x plus 3 times 0 is equal to 18, and we just need to solve for x. So 3 times 0 is 0. This is then 2x is equal to 18. Divide by 2, divide by 2. That is, x is equal to 9. Alright, so what are our x-intercepts? Well, the answer is not 9. X-intercepts are an ordered pair. That ordered pair is the value 9, 0. And so that's the x-intercept. Then to find the y-intercepts, we act similarly, but it's going to be x is equal to 0. So we have 2 times 0 plus 3 times y is equal to 18. That is, 2 times 0 is 0, plus 3y is equal to 18. Divide by 3, divide by 3. Y is equal to 6. But once again, the y-intercept is the ordered pair 0, 6, because we let x equal 0 and we found the y value that corresponds to that. 2x plus 3y equals 18 is what we call a linear function, a linear equation. That is, this thing's going to be a line. So just plot 0, 6, 0, 1, 2, 3, 4, 5, 6, and 9, 0. And now connect the dots. So here we are. Symmetry. So we're going to talk about 3 types of symmetry. So first there's x-axis symmetry. What does x-axis symmetry look like? It looks like a mirror image above as it is below the x-axis. Or if you had a sheet of paper, if you were to fold that piece of paper on the x-axis, if the stuff below the x-axis lines up with the stuff above the x-axis, you have x-axis symmetry. When considering x-axis symmetry, if something has x-axis symmetry, for every point that exists on the graph, a similar point where you change the sign of the y value will also be on the graph. But this is if you know it's already x-axis symmetric. If you want to test and find out if an equation has symmetry, x-axis symmetry, replace y with negative y and see if you get the exact same equation that you started with. If you do, we say yes, we're x-axis symmetric. Y-axis symmetry is this idea that if you had your graph on a piece of paper and you folded that piece of paper along the y-axis, everything on the left-hand side of the y-axis and everything on the right-hand side of the y-axis would line up together with the folded sheet of paper. For every point xy on the graph, negative xy is also going to be on the graph. And if you want to test an equation, replace x with negative x and then simplify that thing and see if you get the exact same equation that you started with. Origin symmetry is this situation where if you have an image and you can rotate it 180 degrees. So if I take this picture and I turn it 180 degrees, is it the exact same picture that you started with, just maybe upside down? And for this one, the answer is yes, but specifically you can also say that for every point xy that's on the graph, negative x, negative y will also be on the graph. And if we want to test an equation to see if it has origin symmetry, replace x with negative x, replace y with negative y, then simplify that equation as much as possible, and if you get the same equation you started with, then you do have what's called origin symmetry. So given the point negative 3, 8, we want to plot that point. First, negative 3, 1, 2, 3, 8, negative 3, 8, that's our point. Plotted. Perfect. Plot the point symmetric with respect to the x-axis, okay? So we're looking for the mirror image across the x-axis. If you folded this in half on the x-axis, where would A land? Well, it would land way down here at negative 8. That would be the mirror image across the x-axis. So that's the x-axis symmetric point. If we want to plot the point symmetric with respect to the y-axis, where would that be? Well, it's across the y-axis, so that occurs right here. This is the point that's symmetric across the y-axis. Now if we want to plot the point symmetric with respect to the origin, what happens? Well, take your image and spin it clockwise or counterclockwise, doesn't matter, 180 degrees. You just spin the picture, turn your piece of paper upside down. And if you do, it's going to end up here. So this is the origin symmetric point. Now another way to do these things is just to swap signs using the definitions we gave a moment ago. Given this graph, we want to find the intercepts. So let's look at our graph. Where does this thing intercept, the x-axis or the y-axis? Well, notice that we don't cross the y-axis, right? So there's no y-axis intercepts. But does it cross the x-axis? Yeah, it crosses the x-axis here and here. So then we just need to write those ordered pairs out. They are negative 2, 0, and 2, 0. So those are our x-intercepts, but they are intercepts. Then it asks the question, is this graph symmetric? Well, does it have x-axis symmetry? If you fold it in half across the x-axis, does it look exactly the same above and below? Do those pictures line up? Yes. So I can say it has some symmetry. What types of symmetry? Well, this thing, if you fold it on the x-axis, these are mirror images of each other. They will all touch. And so this is x-axis symmetric. All right, well then let's ask the question, is this thing y-axis symmetric? Well, if you fold this thing across the y-axis, the stuff on the right is going to line up perfectly with the stuff on the left. So this thing is also y-axis symmetric. All right, then we want to ask ourselves, is this thing origin symmetric? And remember that origin symmetric is this idea that if I can spin the picture, rotate it 180 degrees clockwise or counterclockwise, does it give me the exact same image that I began with? And in terms of the graph, the answer is yes. And so for this one also has origin symmetry. For this graph, we first want to find the intercepts. Do the exact same thing we did before. Look at where we cross the axes. So I see here, here, and here. Those three places are the places we cross the x or y axis. And so the intercepts are then going to be the point negative pi halves 0. Then the next point is the origin, 0, 0. Then the third point is the point pi halves 0. So those are our intercepts. They're all x-intercepts, and then 0, 0 is the only y-intercept. Then we ask ourselves, is this graph symmetric? Okay, so let's first ask, is it x-axis symmetric? Well, look at the x-axis. If you fold this piece of paper, pretend it's a piece of paper, across the x-axis, does the stuff above line up with everything in the stuff below? And the answer is no, because notice that this stuff does not occur down here, and this stuff down here does not occur up here, so this thing is not x-axis symmetric. Okay? What about y-axis symmetry? Well, play the same game, but along the y-axis. So fold it, but then that means that this piece would have to be over here, and this piece would have to be over here, and that doesn't happen, so this is not y-axis symmetric. Then we ask ourselves, is this thing origin symmetric? Well, in all honesty, if you could turn upside down and look at the image upside down right now, you would see that yes, it looks exactly the same as previously, except all the numbers would be upside down. And so this thing does have symmetry, specifically origin symmetry only. For this graph, we want to find the intercepts again. Right here, that's the only one, the only place we cross the axes, and this is the ordered pair, -3, 0. Then, is this graph symmetric? Well, first, let's check x-axis symmetry. Fold it along the x-axis. Does it mirror on top and bottom? The answer is yes. So we do have symmetry. We have x-axis symmetry for certain. Now let's ask y-axis symmetry, but notice that if you look at the mirror images on the y side, the only way this would be y-axis symmetric is if the parabola shape was on the right in the exact same way. So it's not y-axis symmetric. Well then, if you'll turn your head upside down or turn your device upside down and look at it, is the image upside down the same way as it was right side up? And the answer is no. And so this thing is not origin symmetric either. It's just x-axis symmetric. Now we want to draw a complete graph so that it has y-axis symmetry. Well, y-axis symmetry means it just mirrors across the y. So if I have this point 1, -1, then I must also have a mirror point over here. I have this point 2, -4. That means I must have a mirror point over here. Then I need to draw technically the exact same parabola. And it's not perfect, but it's pretty close. So there we are. For y squared equals x plus 81, we need to find the x-intercept and the y-intercept. So let's find the x-intercept. Remember that the x-intercepts occur anytime y is 0. So let y be 0. 0 squared is equal to x plus 81. Now we just need to find the x value. So 0 squared is 0, minus 81 from both sides. I get that x is equal to -81, and so that is an x-intercept is the value -81, 0. Now we need to find the y-intercept. That's when x is 0. So that is y squared is equal to 0 plus 81. That is y squared is equal to 81. So now I need to take the square root of both sides, but remember when you take the square root of a square, this is going to be a plus and a minus. And so that is y is going to equal plus and minus 9. And so we get two y-intercepts. They are 0, -9, and 0, +9. Well, now we want to know, is this thing symmetric to the x-axis? So, if we want to know, is this thing symmetric to the x-axis, what should we do? Well, we're going to replace y with -y. So, we replace y with -y, that is negative y in parentheses quantity squared is equal to x plus 81. Then we ask ourselves the question, does this thing completely simplify in such a way that we get y squared is equal to x plus 81? Well, we have to do the algebra. -1 times y quantity squared is the same thing as -1 squared times y squared. And so then -1 quantity squared gives us +1, and so this ends up being y squared is equal to x plus 81. And so it looks exactly the same as we started, And so this thing does have x-axis symmetry. So the answer to this one is yes, x-axis symmetry. Now we want to test the y-axis. So we're going to do this similarly, but now we replace x with negative x, and then we simplify it. That is, y squared is equal to negative x plus 81. Well, then we ask ourselves, are there any factoring or reduction techniques such that I can make this thing be the same as y squared is equal to x plus 81? And the answer is no. If I tried to factor out this stuff on the right, I would just get positive x minus 81, and that would be equals to negative y squared. So the answer is no, not y-axis symmetry. Then we want to test origin, and this one you just replace x and y with the negative values. Okay, so replace x with negative x, y with negative y, and if it looks the same in the end, then yes, we have origin symmetry. So we have negative y quantity squared is equal to negative x plus 81. But simplify this negative y quantity squared just gives us positive y squared, and then it's equal to negative x plus 81, and so this thing does not have origin symmetry. No, origin symmetry. We want to know what's the x-intercept, what's the y-intercept, is it symmetric to the x-axis, y-axis, or the origin, or some combination. So let's find the x-intercept. Remember, replace y with 0, and so that is 0 is equal to negative 2x divided by x squared plus 16. But to simplify this thing, I need to multiply both sides by x squared plus 16. X squared plus 16. But x squared plus 16 times 0 is 0, and so I get 0 is equal to negative 2x. Then I divide by negative 2, divide by negative 2, and I get that x is equal to 0. So did I find an x-intercept? Yes, I did. Specifically the origin 0, 0. Then the y-intercept, which is going to occur when x is equal to 0. So this is y is equal to negative 2 times 0 divided by 0 squared plus 16. So then this is going to give us y is equal to negative 2 times 0, which is 0. 0 squared is 0, plus 16 is 16. And so I get the same value that I just found. That is the origin, 0, 0. Anytime you have the origin as 1, it will obviously show up in the other because the origin is both the x-axis and y-axis. Now we want to find out, is this thing symmetric to the x-axis? All right, remember to find it symmetric to the x-axis. Replace y with negative y, and then simplify and see what happens. And so this is going to give us negative y is equal to negative 2x divided by x squared plus 16. Well, if I try to divide both sides by negative to move this negative over, the best I can really do is y is equal to negative 1 times negative 2 up there is going to be really positive 2x divided by x squared plus 16. But notice that this thing is not the same, and so this thing is not symmetric to the x-axis. Then let's check y-axis symmetry. That is, replace x with negative x, and then check. So this is y is equal to negative 2 times negative x divided by negative x quantity squared plus 16. And so when we check this one, well, simplification is going to do what for us? This is then y is equal to negative x times negative 2 is positive 2x. Negative x quantity squared is going to be positive x plus 16. And then we look at this and we say, is there anything that we can do to manipulate this algebraically to get to y equals negative 2x over x squared plus 16? And the answer is no. There's nothing that you're going to be able to do. And so this thing is not y-axis symmetric. But now we got to check origin symmetric. So we replace x with negative x, y with negative y. This is negative y is equal to negative 2 times negative x divided by negative x quantity squared plus 16. That's going to give us negative y is equal to negative 2 times negative x is positive 2x divided by negative x quantity squared is positive x squared plus 16. And then is there any way we can manipulate this entire thing to make it look like this thing we started with? And the answer is yes here. Divide by negative 1, divide by negative 1. Then this thing is going to be y is equal to negative 2x divided by x squared plus 16. And look at that, it is exactly the same as what we started with. It's the same. And so yes, this has origin symmetry. For this one, we want to do the same thing. X-intercepts, y-intercepts, x-axis, y-axis, origin symmetry. X-intercepts, y equals 0. That is x squared plus y squared is equal to 49, where we replace the y with 0. Then this is going to give us x squared is equal to 49. Take the square root of both sides. Remember that when you take the square root of a square, it gives you plus and minus. And so this is then x is equal to plus or minus square root of 49 is 7. So our x-intercepts are the values negative 7, 0 and 7, 0. X-intercepts found. Y-intercepts, let x be 0. So that's going to be 0 squared plus y squared is equal to 49. Then we get y squared is equal to 49. Take the square root of both sides. When you take the square root of a square, you get the plus and the minus. That's going to then give us y is equal to plus and minus 7. So then our y-intercepts are the values 0, negative 7, and 0, positive 7. Now we want to test x-axis symmetry, y-axis symmetry, and origin symmetry. X-axis, y with negative y. So that is x squared plus negative y quantity squared is equal to 49. So then this becomes x squared plus negative y quantity squared is really y squared is equal to 49. But notice that when we simplify, we get the exact same thing that we started with. So this thing is, yes, x-axis symmetric. Y-axis symmetric, that's x with negative x. Then this is going to be negative x quantity squared plus y squared is equal to 49. That gives me x squared plus y squared is equal to 49. Once again, we get the exact same thing we started with. So yes, this thing is y-axis symmetric. Then origin symmetric, that is x with negative x and y with negative y. That is, we get negative x quantity squared plus negative y quantity squared is equal to 49. But when this simplifies, negative x quantity squared is really x squared, and then negative y quantity squared is really y squared, and we get is equal to 49. And so yes, it checks out. So yes, this thing is origin symmetric. Also, if you're starting to notice a pattern, origin symmetry is only possible to occur when the x and y axis have symmetry or don't have symmetry. So the answers here have to match for x and y axis symmetry for origin symmetry to occur. So notice in one of the previous ones we had not x-axis, not y-axis, yes origin. Here we have yes x-axis, yes y-axis, and yes origin. So if ever you get x-axis is yes symmetric and y-axis is not symmetric, you could go ahead and rule out and know that you cannot have origin symmetry if you ever have a mismatch of x-axis symmetry and y-axis symmetry. Can't also have origin symmetry. Graph the relation on the coordinate plane. And so if we're going to do that, I'm going to graph the x-intercepts and the y-intercepts. The x-intercepts are at 7 and at negative 7. The y-axis intercepts are at 7 and negative 7. And if you don't recognize it, this is actually the standard form of a circle with the radius of 7. Notice it has x-axis symmetry, y-axis symmetry, and origin symmetry.